So, good morning, everyone. Welcome to the complex session. I would like to share this. Here we go. The first one is and we will talk about an extension of the fair perfection. Thank you, President. Thank you everyone for being present. Thanks for the forward. It's nice to discuss again. Something that's chemical that's I discussed the financial on the story. The point is this already that goals in the workshop. So number one, scale to the dynamic system and the model micrometers towards so that we're looking at surface verities that are, if you remember your engineering courses, in scales of micrometers. And then the second one, which is maybe similar to there's simple films of basically films supposed to be on surface of so these films. So the additive is the most used and what does is form and forms like sliding surface. So for example, on the right side, you see a micro scan from experiments where basically on the left side, you see where it's present, and then on the right side, you see the aims are to this results. We want to be in our so this number refers to extend opportunity to be. This refers to 2 names. And we're going to get into the model in the environmental side, sliding systems and just to illustrate those experiments that get developed against this and then on the bottom explain results for this. So this is a point potential set up boards like this. It's called on this experiment, and the point is that you have a ball that can or doesn't have to be rotating, and you press against the disc that is usually rotating. And you can modify the applied load, the rotation speeds, and various components, and they're all lubricated in some way. And these would be the outputs of the experiments that we experiment with scan surfaces, can measure the thickness of those tribunes that basically grow on surfaces and wear, and so back to that. Quantum mechanics is a very important part of this whole story because to be able to predict how this comes from, how they affect the wear behavior, we need to be able to predict the pressures, temperatures, and so on that actually occur in the contact. And for that, I'm using our model. And it's a very small repeated quantum model that is capable of simulating regimes from the boundary regimes, basically solid, pure contact without major contribution from the lubricants, all the way to a hydrodynamic regime where we don't have any and it's done in instance. Don't forget the third block. So that is basically certain classy film that is slow rotating form of surfaces. And the main idea is that continuously remove air that sometimes this kind of balance of most of the drones and this the removal of film as we have slide. And the substance material of the steel that is not is actually what we are releasing again. And it's a result of the removal of the film, because the film itself contains some bits of the substrate. So there are some iron atoms, but if their concentrations are less than 100%, which basically means that we're not going pure substrates. And important to understand is that the triptylon, as it grows, hardness is decreasing, which means that the wear is going to hardness is decreasing, which means wear is going to increase as it grows. And because of this fact, we have a steady state behavior at a certain thickness because the growth and balance at highs. So about growth. This is quite established approach to doing this, and there's a lot of different work going into determining how this works. So growth is basically an exponential order of variation parameters, and the growth actually depends on the applied shear stress now and the temperature here in the top. For the removal, so this we have one field and there will be the movement from one is where here you might have velocity, you have a very efficient, which is then and the trick with this one is that it's linear, which is certain pressure, and that's the trick, especially when coupled with the fact that our growth term is exponential, and basically what happens if you look at the growth surfaces as, imagine you have a very hot surface, you have very high there, and then the term grows even more between the next time, so you have an even higher pressure, and basically that very hot surface is going to be bigger, that's going to be some that basically explodes surface, and then this will be linear and yes, except you the default. So basically, I implement different removal model for the surface. So basically, depends how we calculate how much surface get removed, and it's basically connected with the blue curve that's here, which is the growth, and basically as the figure is growing, the removal gets higher and higher, following the hardest increases, so on and so on. So I don't want to get too much more than how actually this one has blending from the roots to the flow, and then I basically blend those exponential. And then after we have the removal of the film elements, contains a certain content of a certain percentage of the substrate. We basically multiply it by the assumed percentage distribution per thickness, and thus we actually calculate the wear of the steel. And basically, yeah, that concentration drops off close to the surface of the tube, which makes sense that it's 1 or 100% at the steel, and less. Regarding benefits, they are quite a useful story. So, as I mentioned already, hardness multiple continuums. The reduction of hardness affects again the surface movement rate, but also plasma formations. And the last point was important because it diminishes, which basically cushions the water pressure and acts like cushion. Also, I did something called shear hardening, and the idea is that there's experiments which show that with time and with applied shear stress to on the asparagus where we have growth in zero, those asparagus can become harder. There's a connection to crystallization processes on a theoretical level, but this is the maths of pigmentation. I don't want to worry much of that, but this is just something that's also empirical that helps get good magic experiments each other. This is an important part of the story. The problem is, it's a station of the study. This is both for composition and appearance, I think. And also, what is mentioned that the one is pencil, it expands tens of units per step. Important the composite mechanics because and I'm using method to sequence this. So basically the idea is to solve in several parallel positions, but then basically average out what is going on and what the individual experience feel. And this is an example that's shown where you see 4 different parallel solutions, and basically you can average what's going on. And this is quantitatively and becomes very good with a high number of parallel solutions. This smooths out and becomes interior solution. And also, very nice thing about this is that parallelization becomes full because the parallel solutions are not dependent on each other, which means that you can just throw them in processors, solve them at the same time, and then just work together and average here we'll see then we are an example of this one of this sliding average of parallelization. How it works, and imagine this like a carpet being dragged, and as it's dragged, and the point gets to a certain plane, kind of accumulates a slight amount of scalar field that is in this cylinder. And this is basically by very different modes of different kinds of parallel solutions. So I'm just doing this right for okay, doesn't work. Never mind. Yes, eventually. Yeah. I think. But then I'll just explain that. So here we have when I do this parallel solution thing, how things depends and make difference, how things affect results. And this the idea is what the lab is a solution with the most parallel solutions for this example, and the smallest time step, and this we inclusion is enough parallel solutions if I have a small time step that this are this current experiments. So again, these will be the results that experiment was produced in studies like this. So again, all of this, we are studying the flow of the film on the ball, and the where on the discs there's a slim of where track on the disc. So some experimental parameters that might care too much about, but that there's multiplied. The certain surfaces are transmitting materials, temperatures, and so on. So these are basically my results. My results are the lines, and the experiment results are the speed points. And these 3 lines, x points, present the solutions and temperatures. So here you see for experiments is that in fact you should get more connection with bigger variables, and as a result of that, against and then again, here on the left side, we see one specific on top. You see material. This is magnified in the same direction, so it's not this big. This domain is half a millimeter by half a millimeter, and this circle is 1,500 this big. And then on the bottom, you see where of the disc surface and the orange surface of the see. is basically what we start with, and then eventually it gets formed off, and then simply kind of goes down and down. And basically, if you look at the left, it's sort of big areas which indicate a higher where compared to the right area with 100 degrees Celsius. So now that we have this condition against certain size, it's easy to see how this might work with parametric size against solid parameters. So when we do a sweep across temperature radius, basically it's interpolation of extrapolation. So I basically had 186 Celsius, and then see how it goes for 970, and kind of fits nicely in between these solutions, which is exciting, but it's kind of see. And I also tried simulation of energy film. In this case, we basically right blue line. So basically, it is obviously a zero line on the top graph. So the top graph shows the evolution of the different wall, and the bottom graph shows the evolution of the paradigm on this. And you can see how, in the case of energy film, we get a much higher wear on this than in the case with and this is a study where we vary the sliding speed, the slip basically between surfaces. Either you change the velocity on the ball or on the disk, that affects the wear behavior and to the behavior, and this we increase the slip, which means there's a higher relative speed of the surfaces. We get more wear and thinner and this is very normal loads. So if you think back to the box model, if you increase the shear stress, you get an exponentially higher loads. And pressure is connected to the shear, which is connected to the probe as well exponentially. And with a lower so the baseline solution is the blue, it's 6 Newton solution. And then as we increase the applied loads, we get basically, and also higher wear in this case. This is the opposite. This is what you get when you increase the temperature. And with modified roughness to this, so the parameter specification roughness of this was already used on roughness of this of 130 nanometers, and then I should increase the 360 for that effects. And similar effects like the applied load with steel on a much smaller scale. So it's kind of so ultimately, a detailed model is developed that is capable of showing behavior of certain experiments. Parts of the parts of some of that seems not actually simple to finish. I've done a lot of work on dependence to see what it did, not too much about here, but it's a very cheap aspect of the story. And this is one which I want to send. But ultimately, I think it's very good to study intervals in the next perspective. And for future work, I want to further relations against the result. There's a lot of experiments, luckily available in the literature. I need to actually do small modification simulations with this German model. And I do want to study further each phenomenon in this small area. So, such durabilities, basically, the idea is if there is no more anything in the oil, how long is that thing to last? Then how does the type of gas affects the behaviors? There are basically two different categories, and one of them is that for this, one is this. So there are topics in this area where also again have to design these additives and are each included into some this. Well, this is very good. Basically, one is relevant and one is interesting exchange. Yeah. So thank you very much, Robert, for the nice presentation. So we have time for one or two quick questions from the audience. So this is connection parameter. Steel balls diameter, you get the one that is about 0.3 millimeters in diameter. Then basically I just try to capture weight plus double that. So it's about 1 millimeter, and then you have 200 cells, it's 2 to 3 micrometers thick, or maybe slightly less, and so on. So that's kind of micrometers per something. The question regarding this field of trying to do this field of animals. Because it's not things the scale, and there's some things you do, for example, some things you can get very active measurements, for example, for the layers. For you can scan this quite nicely, but it's very hard to determine with a higher solution, for example, how what the hardness of the surface, like how the name, so these determined result. This is going to be analytical simple, like this is become a laser point gets and then that's going to help with the average where they're so thank you. Let's thank the speaker once again. You have to move for the next presentation that will be online. Please set up, and hopefully Hollie is giving us.
Hello, can you hear me? Hello? You're on mute. Can someone just give me a thumbs up if the sound's okay? Okay, so yeah, thanks for being here, everybody. My University of Manchester, and I'm on an EPSRC studentship with AstraZeneca. I model granular materials using a continuum approach, and today I'm going to talk about. Pardon?
Oh, sorry. Everything okay? You can proceed.
Okay, sorry. Yeah. So today I'm going to talk about approach using OpenFOAM. And the system that I'm going to talk about to demonstrate this is called a granular superstable heap. So to explain what a superstable heap is, I'll first begin with just a normal granular heap. So if you imagine that you've got some sand and you're going to pour that just onto a flat bed, and then as you supply more material to that pile, your pile is going to get wider and it's going to get taller. But what's important is that the angle of this free surface won't change. So for these glass beads here, this angle is set at 22 degrees. For an angle less than 22 degrees, the granular material doesn't want to flow and it's quite happy to sit statically and form a pile. Whereas for angles greater than 22 degrees, this material wants to flow. So you would think that if we took a box and we inclined it 29 degrees, then you would think that all of the material would just flow straight out of the box. But if I play this experimental video here, you can see that that's actually not what happens, and we do get this pile. Is that because we've confined our channel at the front and back with sidewalls, then that means that there's an additional frictional component in the system, which means that material can't evacuate the domain as quickly as it's being put in. So we end up with this material being trapped in the system and forming this pile. And then as this pile begins to grow, it's actually also increasing this angle of inclination even further for this free surface flow, which means that we'll eventually reach this steady state where the flow rate of this free surface flow is equal to the inflow. So material will just flow in the domain, down the free surface and exit the domain, and the pile will remain unchanged. But this pile still can't drain so long as this free surface flow is there trapping it in, because all of the material flowing out is the material that's flowing in. But you can see that once the inlet is cut off, then this pile is free to drain. It wants to, because this angle is steeper than the initial 22 degrees that it wants to remain static at. So the reason that we've been interested in this system is that at the minute, nobody has been modeling the entire time-dependent physical system, because there's no analytical solution. And other numerical methods are just too computationally expensive to try and do something like this. So we wanted to see if we could do it with our continuum model. So to begin with, we'll need a set of equations which describe how our bulk granular material is going to behave. And that's quite difficult for a granular such a wide range of behaviors, and you can see that even in the system here. So you can see we have regions where the granular material is behaving like a solid, where it's static and resisting shear, whereas we can see along this free surface flow, the material is sort of flowing like a liquid. And then in this initial filling stage, in this free-falling jet, the material is behaving ballistically, kind of like a gas. So you can see why a single system of equations which describes all of this behavior is a bit of too much of a task. So what we're going to do is we're going to simplify things and say, okay, the thing we're interested in is this actual heap behavior here. So we're not going to worry about the filling of it at the minute, and we will revisit that later. So we'll remove that gas-like behavior, and we're just going to focus on the solid and liquid-like behavior. So how are we going to describe how this is behaving? So what we do is we say that the solid behavior, you can think of that as behaving like a viscous fluid with a really reluctant to flow. Whereas in this free surface flow here, the material is behaving like a viscous fluid with a much lower viscosity, so it flows much more easily. So this entire system here can essentially be described as a viscous fluid where our viscosity is going to vary depending on. So to begin with, we'll have a system of equations which are just the now. We're going to define our bulk density to be the product of the density of an individual grain times by the packing fraction of all of those grains together. And we're going to assume that that's constant. So our conservation of mass equation reduces to an incompressibility condition. And then we're going to just solve this in 2 dimensions. So we have our downslope and we have our upward normal, which means that the first thing that we need to do to adapt these equations is we need to add back confining sidewalls, because obviously they were essential to create this heap. But because we're not solving in this cross slope direction, we can't apply a boundary condition on those boundaries to say that those walls are there. So we have to incorporate that effect. So we now have a system of equations that describe our system. Viscosity, this is just some sort of fluid viscosity. So we need to write that in terms of some sort of granular properties now. So after applying some constitutive relations, the granular viscosity is given by this quantity here. And what this is basically telling us is that our viscosity isn't really shear rate dependent because we're normalizing by the strain rate tensor, but it's instead pressure dependent. And it's dependent on this mu here, which describes the friction that particles feel as they interact with each other. And this friction isn't actually constant. It's a function of this number here, I, which is known as the inertial number, and that's this dimensionless quantity here. People use that this can take, and we use a form that's given by So we now have a system of equations that are going to describe how our granular material is going to behave, but now we're going to want to apply some boundary conditions to that to completely close and solve our system. But if we look at some time snapshots, so this is the filling in purple and the draining in orange, and these are just contours of the experiment at points in time, you can see that it's really not intuitive where the free surface will be at a given point in time, and there's no analytical solution that tells us where this free surface is going to be. So we can't really easily apply a boundary condition on this free surface if we don't know where it is. So to get around that, we model this system as a 2-phase system where one phase represents being in the granular matrix and another phase represents being in the excess air, so you're just outside of the granular material. And what that means is that this interface now become, the free surface, is now just the interface between those 2 phases, so we don't need to just evolve with the system. But one problem with multi-phase approaches, which isn't limited to granular systems, this is true for all multi-phase approaches in general, is that if you just advect the volume fractions, first panel here, where material is just being injected through this left-hand boundary. And obviously that's really undesirable. So in OpenFOAM, there's an interface sharpening technique, which is where you have an additional term here, which compresses the interface by forcing air towards higher concentrations of air and grains towards higher concentrations of grains. And that's employed in the second figure here in figure B. And you can see that the interface is a lot clearer and sharper in this instance. So it is doing the right does is that you can also see that we get these air bubbles trapped at the bottom of the flow. And that's unphysical in our system because we can't get bubbles trapped in our granular material. So we need a method to evacuate those bubbles from our system. So instead of using the interface sharpening equation that's already built sharpening approach, which is using this equation by Gray and ANSI, and basically this is an equation that's used materials with different properties interact with each other. So we're going to use that here as an interface sharpening technique because it has the same structural form as the OpenFOAM interface sharpening. But what it means is we have free choice of the direction that we choose to force our material in. So we can choose a direction which both compresses the interface as well as evacuates bubbles. So you can see that in this bottom figure here where this is implemented. You can see that we still have this really sharp interface because in this instance, air is just being forced upwards and grains are just being forced downwards. So our interface is still compressed, but because air is now being forced upwards, then that means that there is more realistic with. So this is another system that we're solving on top of our governing equations for the advection of the flow. And then finally, the last thing that we need to address that free falling jet, which we neglected at the start, because we need a way to deliver material. And the rheology that we've used to describe the granular behavior for our heap is not appropriate to be applied to a free falling jet because the physics are just completely different in that sort of region. Free falling jet, but it can produce some sort of jet. So it can just be used as a mechanism to deliver material to our heap. So this is what we decided to try and do. To say that at no point are we saying that this is analogous to any sort of physical free-falling jet. We're not trying to actually model a free-falling jet here. We're just using it as a numerical technique to deliver material to the region that we want. So with that in mind, we said that our criteria for the jet is that we need it to fall stably and coherently. So we don't want it to be moving all about the domain. We want to control where that material is delivered to our domain. And we also need to make sure that the flow rate is conserved throughout the jet so that when we apply a flow rate at the inlet, that flow rate is also what is being received by the heap. So if we just take and we inject into our numerical domain a pure granular phase jet with what happens, and you can see that we're straight away not satisfying this first criteria. Our jet is not stable and coherent, and it's sort of becoming unstable and moving around. And this is essentially because in our governing equations, we're essentially modeling our granular material as an incompressible material. So as this jet falls and accelerates, it accelerates in order to conserve that flow rate. And then that means that it becomes so narrow that it's going to require a really high grid resolution to resolve. And also it can become destabilized by the surrounding air. So that's not really helpful to us. So what we do instead is we create a jet which is mostly air being pushed in with a small amount of grains, but the same flux. So what that means is that our jet falls much slower. And then because it's not accelerating as much as it, and that means that it doesn't become destabilized and it delivers material. So we just need to check that the flow rate through our jet is conserved into the system, and the blue dots are the flow rate through slices of the jet horizontally at points in time, and you can see that those are equal. So we do have conservation through our jet. We have the tools that we need to be able to model a superstable heap in our numerical simulation. Here's our numerical simulation of a superstable heap where the color bar represents the velocity. And you can see that we do get this blue region of static behavior with this free surface flow. So that's a really good sign. We've got a heap forming. And you can see that we do begin to approach this steady state where material is going to flow in across the inlet and out. And then the last thing that we need to make sure is that the system is going to completely drain, because we want to make sure that this is a superstable heap and that it's not just a case that in our numerics, granular material is actually quite happy to sit on an angle of 29. So you can see that qualitatively, we have been able to, really exciting. But now we want some quantitative agreement. So for the right flow rate and for the right physical parameters, how close is our numerical superstable heap to the one that we see in experiments? So what I have here are some photos of our experimental filling on the left and the draining on the right. And then these purple lines are the contours of our numerical heaps at points where there's the same amount of material in the domain. And you can see that there's some slight differences at early times, which we believe are an effect of the boundary condition at the base. And you can see that once the dynamics and the numerics sort of move away from that boundary condition at the base, then we start to see stronger agreement. And then at steady state, we're really, really close to the experimental system, especially when you consider that we're modeling our granular material as a continuum. So we're not modeling every single individual grain and the dynamics of that. We've made some continuum assumptions, and we're still this close to the agreement. So we're really, really happy with this, and the same with the draining. Interested in this because we wanted to see if we could do the time-dependent problem, which we've done, which people aren't doing at the minute. But what a lot of the literature does focus on is the steady state behavior. So now we want to do some steady state analysis to make sure to do the time-dependent problem. We want to have accurate steady state results as well. So to analyze the steady state, then we have 3 experimental superstable heaps here, which correspond to these velocity profiles on the right. And the velocity profile is measured along this free surface flow here when the system is at steady state. So our orange lines are our experiments, and our yellow lines are our numerics. And you can see that we have really, really close agreement here as well. Like, just to point out, a centimetre and a half. So differences that we see are actually really, really small. And obviously the shapes are slightly different. But again, that comes down to the fact that we're using a mathematical model, which on the scale of the entire superstable heap, these are really reasonable assumptions to make. But then when we look really closely on these sort of small, capture the full behavior with our system here. But again, this is still really, really close agreement. Theory, which is given by this equation here. So this is what we expect our numerics to converge to. And you can see that we are pretty close to these. And I don't think that it takes a lot of convincing to believe that we would converge to that. But we're still a little bit off being completely converged on our analytical solution. And essentially the reason for that is that because for a granular system, our CFL condition has this additional viscosity term, which can normally be neglected. But because we're assuming that our static granular material has a really, really high viscosity, this essentially becomes non-negligible, and we have to incorporate this. So when we're in these regions of static material, we have to take a really, really small time step to satisfy the CFL condition, even though there's not actually a lot of dynamics. Even though our grid resolution is really quite refined over the scale of the entire domain, because our free surface flows are so thin, you can see that if you actually wanted to completely resolve these velocity profiles, these is quite coarse still. So we would need an even smaller time step to be able to resolve that completely. So to do this in any sort of like reasonable computational power, we would need some sort of dynamic adaptive meshing technique, which would essentially refine this free surface flow and completely resolve these regions where there's power. But we're all sort of relatively new to using OpenFOAM, and as far as we could see, the OpenFOAM dynamic meshing can only be applied to 3-dimensional systems, and we're not really sure how to implement that in a 2-dimensional case. So if anybody here has any ideas on how we could possibly implement that, then I'd be really interested to talk at some point during the conference or afterwards. That would be really, really helpful. So to summarize everything that I've talked about today, I've shown that we can model granular materials as essentially viscoplastic fluids where our viscosity is dependent on granular properties. And I've shown that we can model the full time-dependent superstable heap system. And while we're doing that, we're also not sacrificing any steady system. But if we wanted to see complete convergence to the analytical solutions, then we would be able to do that within some sort of reasonable computational expense. So that's everything I have to say. Thank you for listening. And if you have any questions, then I'd be happy to answer them.
Thank you, Hollie. We faced some few technical problems. We didn't hear you continuously, but let's see if the audience has some questions, please. So we have time for one question for Hollie. It seems there are none. I have one, Hollie, because you used the 2D approach.
Yeah.
How did you manage to force that in the experimental setup?
So the experimental setup and the reason that the superstable heap even forms in the first place is because the system is so narrow in the first place. So the distance between these two walls is actually only about 3 millimeters. So the reason that we were essentially interested in that is because a lot of people in granular research do a lot of these sort of toy problems, so small scale experiments where they make their systems really narrow. So we sort of looked into this as a reason you have to account for this wall friction effect if you're going to make your system really narrow. Otherwise, you would never see any sort of agreement with your numerics. So it's essentially the experimental system is sort of a quasi 2D system. But the sort of point of that is that then you have to account for that wall friction effect in your 2D model as well.
Okay. Thank you very much, and congratulations for the presentation and the work.
Thank you.
I don't think this will my friend. Yes. Okay. So hello everyone. My name is Bruno. I'm a PhD student at the University of Minsk. Today I'm here to present part of an ongoing work titled "A Plugin for Multi-Fiber Orientation inside OpenFOAM." The outline of this presentation is the following. I will start by describing how to model fibers at different length scales. I'm going to talk about a little bit about the state-of-the-art fiber orientation models. What have we done to implement about the model of the state-of-the-art inside OpenFOAM? What tests have we made to check the accuracy of the implementations, the results that we get, and finally some conclusions and outcomes of this work. So let's start with some assumptions. We don't want to model continuous fibers. I work with injection molding, so we are interested in these continuous fibers that are straight and rigid, and we need to describe mathematically how orientation is classified. So there are usually two ways to do this. You can have a pair of theta phi angles classify the orientation of the fiber, or a unit vector P that will bond along the fiber axis. Now, this unit vector will have a head and a tail, but the fiber in specific you don't have it. You don't know if it's pointing one way or the other. You have two valid choices from this. So whenever you have formulation that deals with fiber orientation, you should take this into account, or this relationship that you can have to selections for the orientation. The motion of a single ellipsoidal particle has been described over a century ago. And the equation that George Jeffrey came up with is the one in the screen, and he assumed the compressibility of the flow, the fluid, no turbulences, neglecting initial inertial and body forces. The particle moves with the fluid, and particles do not interact with each other. Okay. From this equation, you can see the effect of rigid body motion parameter that will quantify the form factor of the particle, which can vary from a disc shape to a cylinder shape, the effect of deformation on orientation, and the term that will keep the unitary length of the unit vector. Now, I told you that I work mainly with injection molding. This is a laboratory part, not an actual industrial part. This is a polypropylene that has 20% of glass fibers, and this is a micro scan of what you get. So you have a huge amount of fibers. This is not even a very heavily filled part, and you can have thousands of fibers per cubic millimeter. So you need a way to describe the orientation of an ensemble of particles. So raise the question, how can I do this for a population of fibers? And if you look into literature, the most accepted answer is, well, we're going to use the individuality of a single fiber, and we're going to use a statistical method to describe this. And this is usually done through a probability density function. This probability density function has a couple of properties. It is defined over a conformational space, which is the surface of a sphere, and it's a symmetric probability density function. And if we integrate over the whole unit sphere, the whole probability should add up to 1. Okay, so maximum 100% of orientation. You can also find evolution equations from the probability density function equation, which is usually known in literature as the continuity equation for fiber orientation due to the similarity of the continuity equation. You have the material derivative of the probability density function is going to be equal to the divergence of the flux of probability of something. If you ignore the dependency on space, just conform with conformational space and time, you can discretize this requirement problem, solve it, and it's a feasible system to solve. If you account for the time space dependency, you have a huge system. You have to discretize this over the unit sphere, space, and time. So you get a very, very big system. Now, one thing we haven't tackled is if I have a very big population of fibers, they are bound to interact with each other. So I need to account for these interactions. And historically, this was made in 1984 by the work of Lloyd and Tucker, who has proposed a phenomenological model to account for interaction between fibers. They based their work on Brownian motion, so kind of collisions that are going to happen, and they have basically created a diffusive flux. The work of Jeffrey, which is the first portion in here, and included the diffusive flux to model the interaction between particles. What is this model based on? You have a Hotarian diffusivity and the gradient of the probability density function. How have they defined this Hotarian diffusivity? It's a scalar quantity, and this is known as an isotropic Hotarian diffusion model, which is basically a phenomenological constant. So a parameter that you obtain from experience to a biological test, and you try to quantify this quantity, and the shear rate. And this is one of the key points of their work because the suspension, if you stop shearing, the orientation should also stop. So this is linked to the deformation of the suspension. Again, if you ignore the space dependency, you can integrate this over a conformational space over time, and you can get plot like this for a single material point, which show you the probability of orientation. Now, this is a very good descriptor, but it has a dimensionality problem because usually you want to apply this to parts at that degree. You don't want to discretize over a unit sphere. You don't want to integrate this over time over space. This is a very big system, and you don't want to pay for that. So it would be good if you have some condensed descriptor of orientation that you can use. And the state of this was started 3 years later by the work of Anderluh and Tucker, who have proposed the usage of moments of distribution probability density function to create what is known as orientation tensors. And you have several orders of orientation. The most well-known are the second order. You have fourth order, sixth order, seven orders, 6, 8, 10, and so on. They are in pairs because it's symmetric, so the all one will. Okay. And you will also find in literature equations for evolution of the orientation tensor. And usually when you derive the equation for the evolution of the second order tensor, you will notice the appearance of a fourth order tensor in the formulation. So you are describing the second order tensor, but you need the fourth order. So you have a closure problem. You have to find some mathematical way to describe the fourth order tensor as a function of the second one. Or if you have a 6, you have to use one order below. Now, you get the concise descriptor. This descriptor is a second order orientation, which is the most well known. You can identify or you can interpret the diagonal terms as the probability of orientation in a certain direction. Okay? But you pay a price for this compensation. The price is ambiguity in the final orientation. What do I mean by this? In the first example, you have 1 in the first one of the diagonal. This means it's unambiguous that everything is oriented in the x direction. But as soon as you don't have 1, you have multiple states that can obtain the same orientation test. In the second one, you have 0.5 and 0.5 in the first two terms of the diagonal. If you have orientation under 0 and 90, plus 45, minus 45, or you solve both, it will yield the same orientation test. So I cannot tell you if you have something that's not 1, what is the actual orientation. Okay. You can use higher order tensors. This just means that you're going to have more variables. This second order is symmetric, so you only have 6 independent components. If you assume that the diagonal is a probability, and you know from the normalization condition that the whole probability needs to be 1, you can describe one of the terms of the diagonal as 1 minus the other 2. Okay? But this is still the state-of-the-art descriptor for fiber orientation. This is what you usually see in commercial applications. So We have seen the first three models. Over the last 40 years, several other models have appeared in literature to compensate for discrepancies in these current versions of orientation. So in 2008, Wang and co-workers noticed that the model used by Hollie was predicting too fast the orientation, so they developed a formulation for slowing down the kinetics of orientation. They were working with short fibers, so the isotropic potential diffusion model was still okay. 1 year later, Phelps and Tucker were working with long fibers, and when you work with long fibers, using a constant, using a scalar quantity to describe the potential diffusivity is no longer an option. You have to use a tensor quantity in order to quantify direction for this. So they have proposed a tensor-based formulation. A couple of years later, several authors have proposed improvements to how you estimate the Rotary diffusion, so different models to try to better account for this. And finally, in 2020, you will have a model that will take one of the previous one and adjust it, the parameters for if you have shear flow or extensional flow, and adapt the parameters and make a blend between both. The ones we have in here in purple are the ones we have implemented inside of the. Okay, now to talk a little bit about the closure issue. This is a known problem. In literature, you will have several simulations that will try to tackle this problem. And to implement this in OpenFOAM, you will have mainly two approaches. Either you acknowledge that the product, because in OpenFOAM usually we have four-color tensors. You have something for fully symmetric tensors. You don't have 9 components, here you are limited to that, and you have to use some extent. If you want to use something else, you don't have even a four-color class. Okay? So you can either acknowledge that this product will yield a second-order tensor, and you can try to write down these expressions as second-order products. And if you do that, good. If it's not possible, then you're stuck. Or you can also acknowledge that this contraction yields a second-order tensor, and you can use symbolic computation to do whatever you want in fourth-order tensor, and then compute the contraction. This is what we went for. So I'm going to give you the example with just to explain this a little bit with a hybrid closure. Hybrid closure is a blend between a quadratic closure and a linear closure. Quadratic closure is exact when every fiber is aligned in one direction. Linear closure is exact when everything is random. So you are using like a blending coefficient between one state and the other. This blending coefficient should be an invariant of the orientation tensor, and it should be 0 when everything is aligned and 1 when everything is random. So the authors went with the determinants of the second order orientation. So how have we implemented these contractions for fourth-order tensor? We have created a Python script in symbolic computation, where you'll see in line 6 that we are defining something called compute hybrid closure. We have created several routines to do the permutations of ANTIWEAR where needed. We are leveraging the functions in SymPy, and then we are just doing the contraction between a second-order tensor and a fourth-order tensor. Okay? And afterwards, we are just using a routine that we created to very well take my product, remove all the unnecessary operations, just give me what I need. And this will build you a C++ function, which you can copy and paste into a function in OpenFOAM, and it will basically compute this product for you. Okay. How have we implemented this inside OpenFOAM? We have created a class for fiber orientation models. We have the models that we showed before with purple. We have a couple of closures that are the most used in commercial software, and we have built this into a class for fiber orientation. How are we envisioning that this class would be used? You have a incompressible solver. You're going to solve another steps, convert your local fields very well. We're going to plug this inside a function object. And when you call the function object the execute block, it's going to call the solve statement of the fiber orientation class. It's going to solve the system for you. What do you need? A dictionary under the dictionary of functions inside control thing. We're going to create our function object. You're going to define just what model do you want. Fiber general parameters like the closure model, and fiber specific model parameter. We'll put this here. After each step you have done your incompressible sort, we're going to solve the fiber equation. Now, what is this implying? It's basically a one-directional relationship. So flow field will influence fibers. Fibers will not currently influence your flow. This is the working practice. Now, how have we tested this? Currently, our closures only work for 3D flows, and we have tried to mimic with 2D or putting some symmetries in order to have a 3D structure to make it comparable. So we have went to literature, created a Python utility just to integrate the orientation tensor, compare the results with results from literature, and now we're trying to replicate this inside OpenFOAM. So we are seeing here a setup for a case of simple shear, and in this setup, every line or every streamline here is going to yield you a portion of the curve of the orientation. We're just going to look at the other theories. The rest are not relevant for this comparison because they will be in a very small portion of the curve, and you'll see this in a second. What have we done for the setup? Different models, different closures, mesh refinement study. What do we want to see? As we progressively refine the mesh, we want results closer and closer to the Python curve that we are assuming to be the true results, because we have compared this with the results from literature. They approximate very well, so we're going to use as a benchmark. A more close problem to injection molding is to deploy the segregated disk. You have an analytical solution for the velocity field. You can impose this, choose a model, same concept of mesh refinement. What we want to see as we progressively define the mesh, the results should be closer and closer to what we are obtaining from literature or from our Python utility. And these are the results. So under simple shear with a hybrid closure, you will see for the coerced mesh, you'll have some mismatch between the components, this is to be expected. As you progressively refine the mesh, they will basically perfect the fit on one another. Okay, and what we were seeing before, the different lines are streamlined, so as higher as you go, the shorter you are in here. It's not relevant to see these results, so we'll just take the ones that have the most portion of the curve. Same thing for another closure, the IPOF closure. You'll see a mismatch or some mismatch in the coerced mesh. As you progressively refine the mesh, you'll basically see a perfect fit between one model and the other. And for different models, these are just one component that should not have many slides showing the same thing. As you progressively refine the mesh, you'll get the same kind as everything is fitting the Python utilities. And these are also the results for the segregated disk. In this case, we are integrating over the radius. So you are seeing results as close as possible to 0.1, 0.2 in normalized thickness. So you will see also for the coerced mesh, some mismatch in the curve. That's to be expected, but as you progressively define, this will be created in a perfect match within your results. So we have made some experiments with other solvers. This is the usage of PeopleFOAM for an extrusion die. Have a die, you have some flow, very well. You plug in the solver in here, and you can get orientation result without carrying the orientation solver inside PeopleFOAM. It's just a plugin, and you can put in which solver you want. And we have also made this for multi-phase flows, because I will use this for injection molding. I need this to work with multi-phase flow, and this is the test case of inter-isothermal where you have a dog bone specimen. And I don't know if you will see it here, but you'll be able to appreciate it in the convergence region here. You'll have an increase of orientation, and in the divergence region, you'll have a decrease in orientation. This is to be expected. And we also have made a similar thing for an edge-gated plate. We still have some nuances to take care in here, because we have a problem, or not actually a problem, but consideration to make when we start to evolve the orientation tensor. As soon as you have 0.01% of polymer inside, 0.5, full thing, depends. We are still taking care of that consideration. So, as a conclusion of this work, we have created a framework for modeling fiber orientation. We are taking care of the fourth order with a second order contractions through symbolic computation. The framework is plugged into a function object, which you can use for whatever incompressible solver you're using. The implementation was verified with the Python utilities, and it was verified with data from literature, but we still need some fine tuning for multi-phase flows, and we still need to check some of the influence of the discretization scheme on tensor quantities. Okay? We have used the quick discretization in here, but if we have a better, or at least second order discretization scheme for tensor quantities, it would be better. And we are still working on implementing the influence of orientation on the flow. So we are aiming to use Again, we are aiming to leverage function object functionality of OpenFOAM, so that if you use this functionality, we'll introduce the source term in the momentum equation with the contribution from the orientation. But this is still not yet there. And these are the references in case you are interested in reading something from our orientation. And thank you all for your attention.
Thank you, Bruno, for the nice presentation. And we have now room for some questions. Okay. And when Bruno, are these solvers or these plugins available for the public?
If you wait 2 months, which should be available on the videos, but yeah, they will be made available with the best case, then to be able to verify and sometimes like that. The code is not to be working.
I took the risk to get the answer. The paper is in your desk. Please read it. It will be published in the OpenFOAM journal, or at least to be submitted to the OpenFOAM journal. And so, it will be developed. Thank you, Bruno. Thank you. Any other questions? So if not, please. Thank you. Next presentation is a joint work of the SOPREPA and the University of Minas, and it will be presented by João Vidal from SOPREPA. It's one.
Good morning, I'm João Vidal from SOPREPA. I work at SOPREPA, is a polymer extrusion company. First, I will give a brief outline of this presentation. I will give a brief introduction, the motivation for this work, the new approach that we developed, some case studies, and again, the conclusions and the future work. Polymer extrusion is divided in 3 main steps: on-off, calibration, and extruder plus extrusion die. In the extruder plus die part, we form the material. We melt and form the material. The calibration, we cool it and define the cross section, the final cross section of the profile, and in the final we cut it to the desired length. The motivation for this work is that we have a profile and we know the material, we know the linear processes that we want to extrude, we know the typical temperatures that we will apply to the die, and we want to know how to model this system. Right now, the temperature is controlled by reading the temperature in the thermocouple and turning on or off the heaters. But in the state of art of simulation this process, we are applying the temperature in the walls of the flow channel. And we apply the mandrel, this part side here, insulator. And the question is this make any difference to the modeling of this process? And we don't know. This is where all these challenges come to me. Professor João asked me if I could model this process. I said, great, let's do it. Then I put it to the Google Translator, and this just means that you want to have some good words to present PPS and OpenFOAM Workshop. Now let's go to the work. What we did. In OpenFOAM, we have the CHT fluid foam solver, it's a transient compressible for fluid insolation, thermal heat transfer. The solver didn't fit our needs. We needed incompressible solver without turbulence, and for that we developed our so-called CHT derivative component. We also have a new boundary condition. For that, what we did, we are solving the fluid mass energy conservation equation and the solid, and after we add. So this is the part of the boundary condition. We need to create a new boundary condition to model the ethers, and for that we use the external wall heat flux temperature, and we added a PID function that will control the behavior of that ethers. If the PID function is below zero, the ether will be on, otherwise it will be natural convection. So the main additions that we did to the code was to get the sensor boundary ID, sum all the temperatures in the surface of that patch, get the boundary area, calculate the average temperature, and then calculate the PID function. So, and then to model our system, we start by making our map in Snapdragon Mesh. We get the data for the rheology of the material by experimental trials, and after that we need to start know how to assess the results. For that, we divided the outlet of the die, the flow channel, in elemental sections, and we compute the objective function that will need to be minimized, and if it's zero, it's the rest of the result. Okay, for modeling the CHT case, we apply mainly the difference is that we are using a metal wall interface, and we apply external wall PID, the new boundary condition, to the ethers place. For all the surface in the die, we apply natural convection. So after this, we need to validate our boundary condition, and we can see that we are able to get the feed, the temperature feed from the thermal couple, and the boundary condition is working as expected. When the temperature goes below the set temperature in the controller, the heater turns on and the temperature goes up. So we were able to assess this boundary condition. Then we assess the flow channel in the conventional way. The typical, as already told previously, we fix the temperatures in the flow channel walls, we fix the inlet velocity, and then we compare the temperatures, the results. And we can see that in the conjugated transfer model, we got higher temperatures than the one set in the current state-of-art simulations. Knowing this, we developed another approach, the CHT plus the conventional approach, where we read some measurements on the surface of the flow channel and we apply it to the wall as the conventional way. We see some big difference, like in the case of the adapter, we get 4 degrees is considerable difference. And one thing that you can already tell is that the mandrel is insulated. This was not studied in the literature before. We now know that we can use insulated, and is a good approach for this. Okay, another result of this study is that we are able to, after a while in the process, we get the same result as experimentally. That is, the on-off behavior of the ethers doesn't affect the process. The oscillations of the process are residual and doesn't affect really the quality of the profile. So in the temperature field in that outlet, we get considerable difference from between the conventional and the CHT approach. We see that the conventional way is more restrictive to the flow as we get more lower temperatures at the walls. For the velocity, we also can see some difference that in some specific points that are the effect of the difference of the temperature at the walls. So for the pressure, this result, we didn't say it experimentally, but the results are more or less the same. The difference are not that big for the process itself. So, objective function. We see that we get higher temperature. We get a big difference on the elemental section 7. And what we think is the effect of this is because this section is all surrounded by walls. And as we are imposing lower temperatures, higher temperature in the case of the CHC plus conventional approach, all around this elemental section, it promotes the flow back section because it decreases the temperature, it decreases the viscosity, and now we get higher flow rate in that section. So, conclusions. We were able to develop a new CT solver in OpenFOAM. The solver was tested with an industrial case. The message to take home. It's appropriate to assume that the mandrel is insulated. We can model it is insulated. There are clear difference in temperature fields, and the impact of that temperature in the flow can be considered. And we should, as a observer, we should assess this approach with another system and it will get us. Last but not least, for performance solution go to Iberia from Guimarães will be in November 2 and 3.